recovery team can make a safe approach to the spacecraft to begin the process of erecting the front porch. In 25 minutes from now, the entry team of flight control now. They're in their post-sleep period, reviewing morning minutes into the flight of integrity. This is Mission Control Houston at a mission elapsed time of 8 days, 17 hours, 51 minutes into the flight of integrity on the Artemis II mission. The astronauts were awakened aboard Integrity about an hour ago. They're in their post-sleep period, reviewing morning messages, getting a bite to eat, completing the stowage of items in their crew cabin. As everything is all set, the stage is set for their return to Earth this evening with a splashdown of the Pacific off the coast of San Diego 7 hours and 40 minutes from now. Here in the flight control room, known as the White Flight Control Room, a shift handover has been completed. The entry team of flight controllers now on duty, led by Flight Director Rick Henfling. Henfling has trained with this team for more than 2 years for this day. He will be joined on console by spacecraft communicator Jackie Mahaffey. Astronaut Stan Love also will be by her side as a second set of eyes as Integrity barrels home, completing a mission that will have spanned 694,481 miles from launch to splashdown. In the shift handover, no significant issues were reported. The vehicle is in great shape, and the weather at the splashdown zone couldn't be better. Winds are forecast to be 10 knots at splashdown, wave heights less than 4 feet, and the wave periodics against the capsule as it bobs in the Pacific Ocean about 17 seconds. We are expecting a few broken and scattered clouds, but that is not an issue. Integrity is coming home through the law of orbital mechanics. The next major milestone for Integrity's astronauts and the flight control team here in Houston will be the RTC-3 burn. That is the return trajectory correction number 3 burn. That is scheduled 2 hours and 25 minutes from now at 1:53 p.m. Central Time. It's an 8-second firing of the reaction control system jets to essentially fine-tune the path of Integrity down the corridor for its entry into the Earth's atmosphere. There will be a change in velocity of 4.2 feet per second. That is the last major maneuver of the mission. The crew will continue to configure the crew cabin. They'll climb into their launch and entry suits later today and move into their entry checklist. So this is a good time for us to run down all of the key milestones and all of the key numbers that you'll be hearing reported as we move into the final phase of this 9-day mission. And the crew climbing into their launch and entry suits. We will have NASA Plus coverage joining in a simulcast of our 24/7 YouTube coverage at 5:30 p.m. Central Time, 6:30 p.m. Eastern Time. At 6:15 p.m., Integrity will switch communications loops and the strings for communication from the Deep Space Network, which it has been on since the translunar injection burn the day after launch. We will transition from the Deep Space Network to the Tracking and Data Relay Satellite System. At 6:33 p.m., the crew module and its 4 astronauts will separate from the European service module. And at 6:37 p.m. Central Time, these are all Central Time, we will conduct about a 19-second raise burn. Now, if you think of yourself sitting in a recliner and tilting backward, this raise burn gently raises the aft end of the vehicle. It is our last opportunity to dial in a flight path angle before entry interface using the roll thrusters on the crew module. This will sweeten the angle of attack, if you will, the orientation of the vehicle as it enters the Earth's atmosphere, with the idea in mind of reducing any excessive heat stress on the heat shield in this deliberate opportunity that we have selected to try to mitigate any buildup of excessive heat on the aft end of the vehicle. Once the raise burn is complete, we will enter the first traces of Earth's atmosphere at 6:53 and 31 seconds p.m. Central Time. At that point, we'll be at an altitude of 400,000 feet, traveling 34,882 feet per second, with a range to splashdown of 1,701 nautical miles. Just 24 seconds after entry interface, traveling at that velocity, we will begin a 6-minute blackout period due to the ionization, the buildup of plasma around the spacecraft that will prevent communications and data from being received here in Mission Control. Again, that blackout scheduled to begin at 6:53 and 55 seconds p.m. Central Time, about a 6-minute blackout. We'll be carefully monitoring a call from Capcom to the crew as we exit the blackout. That will be our first communications with the crew following that 6-minute period. The blackout scheduled to end right around 7 p.m. straight up. That's Central Time. That'll be 6 minutes and 25 seconds after the start of entry interface. At that point, we will be at an altitude of 157,406 feet off the Earth, traveling at 13,342 feet per second. Range to splashdown at that point will be just 147 nautical miles. There will be a series of roll reversals, rolling, this is computer commanded, to roll the vehicle to the left and back to the right to bleed off excess energy, all part of the planned entry profile for Integrity and its 4 astronauts. We are expected to go subsonic, meaning we will break the sound barrier over the Pacific in this trajectory that will carry us from southwest and northeast across the Pacific Ocean. We will go subsonic at 7:02 and 25 seconds p.m. Central Time at an altitude of 59,000 feet, traveling just 971 feet per second. So you can see how much the velocity of Integrity will decelerate based on its speed and the interaction with the Earth's friction in the atmosphere. At that point, a series of parachutes will begin to deploy. The first deployment will be the forward bay cover chutes. These are a series of 3 parachutes, each parachute approximately 100 feet long. The first forward bay cover parachute deployment will occur at an altitude of 24,000 feet. As the spacecraft has descended to a velocity of just 479 feet per second, and we will be within a mile, 1 nautical mile of splashdown at that point. In rapid fire succession then, we'll deploy 2 drogue parachutes used to slow and stabilize the crew module during descent to establish the proper conditions for main parachute deployment that will follow. A trio of pilot parachutes then deploy. They'll be used to lift and deploy the main parachutes from the forward bay of the crew module. That's the top portion of the crew module. And finally, 3 large main parachutes will deploy. The main chutes are scheduled to deploy at 7:04 and 44 seconds p.m. Central Time at an altitude of just 5,400 feet from splashdown. The velocity for the astronauts aboard Integrity at the time of splashdown expected to be just 19 miles an hour. So in just 13 and a half minutes from the start of entry interface to splashdown, we will have decelerated from what is expected to be a peak velocity of some 23,783 miles an hour to just 19 miles an hour for a gentle splashdown. One of the important points that we've been explaining and that we'll be looking for later today is the comparison between the entry for Artemis I, which was uncrewed, and today's entry for the Artemis II astronauts. On Artemis I, we had an entry range of 3,178 nautical miles, and we used what was called a skip entry profile, where we dipped into the atmosphere, then dipped out, and then dipped back in. That lasted about 20 minutes for entry, and it induced a higher total heat load on the vehicle. Now, on Artemis I, we flew that trajectory, and as part of the routine post-flight inspections and video analysis, there were areas of mechanical char liberation that were observed, which was not expected. As we explained yesterday, it's worth explaining again today, and we'll do later today as well. The chemical decomposition of ablative heat shields is fully expected. The mechanical liberation of the char was not expected. The chemical decomposition occurs as the heat shield material heats up and decomposes, the process called pyrolysis, which generates gases during entry. The generation rate of that gas is a function of the temperature of the heat shield material, which is known as avcoat. As the gases are being generated, a layer of char is forming on the surface of the heat shield. That char is porous. Now, ideally, what you want to have happen is for the gases to escape through the pores in the char layer faster than new gas is generated. But on Artemis I, we found that the temperature profile experienced by the heat shield and on the heat shield was such that this was not happening on areas of the heat shield with less porous avcoat. That resulted in a pressure buildup under the surface of the char layer, and when the pressure gets high enough, the portions of the char layer would liberate from the heat shield. That's what we observed. As a result of all of this, NASA gathered experts from across the agency and private industry, including establishing an independent review team to investigate this issue, and after extensive analysis, everyone agreed with the conclusion that we should plan to fly a shorter entry trajectory to avoid a temperature profile conducive to high rates of gas generation as that avcoat chemically decomposes. Now, for Artemis III and beyond, we're redesigning the heat shield, different heat shield, and redesigning the manufacturing process such that we will have material that starts out more porous and will allow a more efficient gas dissipation as that char layer forms, which will be a critical feature for a longer duration skip entry trajectories returning from the south pole of the moon. The bottom line of all of this is today, instead of a 3,178 nautical mile entry range, we're targeting a 1,701 max entry range to our splashdown zone off the coast of San Diego, 1,701 nautical miles. We're using a lofted entry profile. That's being done through the raise burn. The duration of the entry is about 14 minutes rather than 20 minutes, and that induces a much lower heat load on the heat shield to allow it to do its job to maximum efficiency. Passing second, now just 54,000 miles from Earth, and the distance traveled by Integrity's astronauts since they arrived at the moon earlier this week. We are currently 7 hours, 10 minutes away from splashdown, a high-speed entry back into the Earth's atmosphere, awaiting Reed Wiseman, Victor Glover, Christina Cook, and Jeremy Hansen to wrap up a mission that will have logged from launch to splashdown 694,481 miles. That, of course, includes that high Earth orbit that carried Integrity to an altitude at apogee of about 43,000 miles above the Earth for the first 24 hours of the mission to enable flight controllers to ring out all of the systems on Integrity and collect data that gave them the confidence to give approval for the translunar injection burn that sent the crew on its way to the moon and an historic flyby of the lunar surface.